So in this video, we are continuing our discussion of section 6.3 on partial fractions. We have moved on in day 2 of this lecture to consider some examples which show the full process of using a partial fraction decomposition to evaluate an integral. In example 5, which is the first full example like this, we have been asked to evaluate the integral of t squared plus 8 over t squared minus 5t plus 6. Now remember, with partial fractions, oops, that didn't work. Here we go. We first need to check if the fraction is proper. So the degree of the numerator is 2. The degree of the denominator is 2. But we need the degree of the numerator to be strictly less than the degree of the denominator. So this means that it is not proper, because the degree of the numerator is not strictly less than the degree of the denominator. Okay, so if it is not proper, this means we need to use long division. So this means that we are going to take t squared minus 5t plus 6, which is our denominator, and we're going to divide it into t squared plus 8. Now remember, with long division, we are going to insert any missing pieces that we have, so that would be plus a 0t here. Now we need to multiply t squared by 1 in order to get t squared. So we will have a t squared minus 5t plus 6, and we are going to subtract this. The t squareds cancel. We end up with a positive 5t when we distribute the negative. And then we'll have 8 minus 6, which is going to be plus 2. Now this, the degree is less than the denominator. So this means it's our remainder. So we're going to have plus 5t plus 2 over t squared minus 5t plus 6. So then, the integral of t squared plus 8 over t squared minus 5t plus 6 dt is equal to the integral of 1 plus 5t plus 2 over t squared minus 5t plus 6 dt. Our first term we can integrate, that's just going to be a t, but our second term we can't integrate yet. We're still going to have the integral of 5t plus 2 over t squared minus 5t plus 6 dt. So for that, we're going to have to find a partial fraction decomposition. So we're going to come back to this integral, but for a little while we're just going to find our partial fraction decomposition. So 5t plus 2 over t squared minus 5t plus 6. Now we need to work through the steps of setting up our partial fractions and finding the values of our undetermined coefficients. The first thing we do is factor the denominator. So that's going to be t minus 3 and t minus 2. Then we set up our partial fractions. Both of the factors are linear, so we're just going to have one letter in the numerator. So we'll have a over t minus 3 plus b over t minus 2. Now we need to get rid of the denominator. We're going to do this by multiplying the left side and the right side by the factored denominator. Factored is more helpful because things will cancel easier. So on the left, we have no denominator. So we just have 5t plus 2. On the right, we will also have no denominator, but only certain pieces are going to cancel. The t minus 3 will cancel for the first term, so we have a times t minus 2. The t minus 2 will cancel for the second term, so we'll end up with b times t minus 3. And now we need to distribute everything on the right and then combine our like terms. So we get at minus 2a plus bt minus 3b. Our like terms, we have an a plus b times t, and then plus a negative 2a minus 3b. Now the reason why we do this is we are going to match up our terms with, or the coefficients of like terms. So we should have that 5 and a plus b are equal to each other, so a plus b equals 5. We should also have that 2 and negative 2a minus 3b are equal, so negative 2a minus 3b equals 2. So now we have a system of equations, 2 equations and 2 unknowns. I'm going to use some elimination to solve this. So multiplying the first equation by 2, we'll get 2a plus 2b equals 10, negative 2a minus 3b equals 2, and adding them together, our a terms will cancel. We'll be left with b equals 12. Sorry, negative b equals 12. So then b equals negative 12. Then taking this and plugging it back in, a plus b is equal to a minus 12, which should be 5. So a is going to be 17. So this means that 5t plus 2 over t squared minus 5t plus 6 is equal to 17 over t minus 3 minus 12 over t minus 2. Now, one quick thing I want to say before we go back to our integral. If you had switched the order of your factors here, which would have then resulted in a switched order of your partial fractions, that would have been perfectly fine. The end result would have been that your a and your b values would have been switched, but you still would have ended up with the same 2 fractions at the end, okay? So remember that if you factor things in a different order and you set up your partial fractions in a different order, you will still get the same equivalent answer at the end. It just might look a little different. Okay, so now that we have our partial fraction decomposition, this means that we can go back to our integral. So we had the integral of t squared plus 8 over t squared minus 5t plus 6 dt to begin with, but we already did a little bit of work. We did some long division. We had one term that we ended up integrating to t already, and then we had the integral of 5t plus 2 over t squared minus 5t plus 6 dt. Now that integral we can rewrite as the integral of 17 over t minus 3 minus 12 over t minus 2, and all of that dt. To integrate these 2 partial fractions, you could split up the integral if you would like. Potentially do a very simple u substitution for each one of the denominators. You would need to do different letters if you did it that way. So like, let's say u equaling t minus 3 and w equaling t minus 2. But if you notice, both of the derivatives are just dt. So that's simple enough that I don't care about writing out the details there. We can just go ahead and integrate straight from here. So we get this is equal to t plus, we'll have 17 natural log absolute value of t minus 3 minus 12 natural log absolute value of t minus 2, and then plus c. So let me just pull this integral down on the left so that we have our final answer here. And that is how you do a partial fraction decomposition, the whole process to help you evaluate an integral of a rational function.